All right, so our next topic is flip-flops. And usually when I teach this course in the spring semester, uh, the timing matches very well, because when people are thinking about flip-flops, I just start talking about flip-flops, and it matches very well. And in the fall semester, it's quite the other way around, because we are trying to pack up our flip-flops for the year, and we are now starting to talk about flip-flops. Um, a fun fact: there is also a flip flop lounge. Most of you might know this. That in our department on the sixth floor of JEC, we have a flip flop lounge. Unfortunately, we cannot use it this semester, but it is also referring to the same component, flip flops. Let's see, what is the difference between a latch and a flip flop. And the basic difference is you get more control over when the output can change. That's it. That's your major difference. So let let me write how we are building up on the latches. So latches were basic sequential elements, right? And we looked at three of them. We looked at SR, data, JK, right? Three latches. These are level sensitive devices, level sensitive. And I'll talk about what that level sensitive means in just a minute. They are also called level sensitive or semi synchronous. Because there is some control on when output can change. And from earlier, if you go back to your latches lecture, you will see that when we made C input as 1, that's when we were allowing the output to change. So we had the ability to change. We had some control over when the output can change. However, that control was not very precise in timing, because C equals 1 indicates that as long as C is at the level 1, my output can keep changing, right? So if I go back over here and look at this timing diagram, you can see that as long as C was 1, the blue regions, my output kept changing, right? So I had some control over when the output can change, but that control was based on the level of C as opposed to the edge of C. That's what flip flops give us. Flip flops are edge sensitive devices. So you have a lot more control over when the output can change, more control over when Q can change. We can start saying things like, I want the output to change only when C goes from 0 to 1, or I only want output to change when C goes from 1 to 0. That is called being edge sensitive, and flip flops give us that. These are edge sensitive devices, and these are synchronous because they are in sync with when with the control input C or clock. So that's what we are talking about. We are going away from latches to make flip flops, and the best way to do it is connect two latches back to back, and that's it. That's how you make a flip flop. One latch, another latch, back to back, you get a flip flop, and we'll talk more about that. But that's essentially what it is. The main difference is level sensitive versus edge sensitive. Now, because we have edge sensitive devices to build, our uh, block diagram of sequential circuits is going to include the clock. The clock input is going to be an input specifically for the storage elements, and we need to explicitly talk about that now because it matters when the clock goes from low to high and high to low. So that is going to be explicitly shown in every flip-flop design, the clock input. What is a clock input? Well, it's a periodic external event, right? And this is generally generated using a crystal oscillator, for example, 100 megahertz. What is that? A square wave that is periodic, is low, high at that particular frequency. Why do you need it? Because you can keep every event in a particular design in sync with a master timing event, the clock, right? So if you want everybody to sort of follow a particular timing pattern, then you need one master clock, and that clock is what we are using here to control when the output of a flip-flop can change, or when the output of our storage elements can change. Let's take a look at that clocking event, the clock signal. You guys must have seen a clock in other courses as well. It's a periodic signal, it's an AC signal that goes high, low, and so on. But as it is going from high, low, it can go from high to low, which is called the high to low edge, or the falling edge, or the negative edge of the clock. And it also goes from low to high, which is called, that particular edge is called low to high edge, or the rising edge, or the positive edge. I will be more or less focusing on the terminology at the very bottom here, negative edge and positive edge, meaning the edge of the clock that goes from high to low versus low to high. You see, this was when C was 1, right? And this was when C is 0. For latches, the output could have changed here. But for flip-flops, the output can change only here. So you get very, very precise control over when the output can change. That's the main difference between latches and flip-flops. All right, everybody okay with the terminology here? Low to high, falling edge, rising edge, positive edge, negative edge. I assume that you guys have seen some of this in other courses, but we will be talking a lot about clocks and their edges in the context of flip-flops. Now, some other parameters about clock. Again, this is going to be something that you guys have seen before. A clock signal can go from low to high and high to low, and it is going to be periodic. What is the period? The time period of a clock is simply the time it takes for it to complete one cycle. In this case, it is going to be T high plus T low. That is going to be the time period of this particular clock. How about the frequency? The frequency is going to be 1 over the time period. So in this case, it's going to be 1 over time period is T high plus T low, where T high is the time for which it is on or high, T low is the time for which it is low or off. So frequency is going to be 1 over the time period being the sum of those two times. What is the duty cycle? Duty cycle is expressed as a percentage of time for which the signal is in the high state. So T high divided by time period times 100%. That is going to be your duty cycle. In this case, so if I asked you guys the duty cycle of the signal clock, what would you guys guess that to be? Just guess some number. All right. 60% I think is a reasonable number. But I hope, why 0. 0.4? It doesn't look like 0. 0.4. The high time seems to be higher than the low time. 0. 0.7. All right, 0. 0.7, 0. 0.6, or 70%, 60%. You express that as a percentage. So 70%, 60%, 65%, all these seem to be very reasonable estimates. But you would never guess that to be lower than 50%, right? Because it is visually you can say the high time is more than the low time. So it has to be more than 50%. Is the percentage of the time for which it is high. All right, now let's talk about the active low clock. Active low clock, everything is flipped. And the way you compute duty cycle here is percentage of the time for which it is low. Exactly the opposite. That's the active low clock. Now there is also very clear indication about when the state or the output of the flip-flop can change. You can see here the state changes occur here. So the output of the flip-flops can only change here or here or here or here or at these times, depending on whether the flip-flops are positive edge triggered or negative edge triggered. So they can be sensitive to positive edges of the clock, or they can be sensitive to negative edges of the clock. Only one. We again have the same setup and hold time requirement, even for flip-flops when you're trying to store things. If you have a clocking event that happens over here, right? Let me highlight that. The clocking event is right there. The input to the sequential elements, the flip-flops, cannot change before that and after that. So if this happens at, say, 10 seconds, and I say that just for the sake of discussion, I say setup time is 1 second, hold time is 2 seconds, right? If I say that, these numbers are not realistic, I'm just assuming these numbers. That means that the input to the flip-flop cannot change before the 9-second mark and after the 12 seconds mark. They can change it after or before 9. So before 9 is fine, after 12 is fine. But if my setup time and hold time are 1 and 2, then and my clocking event happens at 10 seconds timing mark, then those will set up the minimum timing requirements for change in the input before and after. The same sort of definition that we looked at earlier, but that applies even here. So let's take a look at what we have been, how we have been constructing our latches, and now to flip-flops. What I'm trying to convey is we have always built upon the first bistable sequential element that we looked at. The first thing that worked for us was the NOR based SR latch, and everything else was built on top of that. So using the NOR based SR latch, we made a enabled or gated or clocked SR latch. And then we also looked at the NAND version of the enabled SR latch. Then we looked at the D latch. Then we looked at the JK latch, right? So everything was getting built up on that NOR latch analysis, which relied on 4 things: set, reset, store, and the not allowed, which created a problem which we were able to solve using either the enable signal or the D latch. We were able to solve that. Now, in order to go from a latch to a flip-flop, we need to connect the latches in a master-slave configuration, back to back. The claim is this: if both components, the master and the slave, are latches or they are level sensitive devices. If I connect them in a back-to-back configuration and I have a clock input that gets complemented once for the master and complemented twice for the slave, which means that they are each responding to the different level of the clock, then I get edge sensitive behavior. That's my claim. So what I'm going to do first is this. I'm going to start off with the analysis of the master slave D flip-flop. I'm trying to make the master slave D flip-flop, or simply the D flip-flop, data flip-flop, using two data latches. And I'm claiming that if I connect them in this way, the output of one driving the input of the other, I will be able to achieve edge triggering. I hope you all agree that the first one and the second one, being a latch, being a data latch, they are going to be level sensitive. So when I say D latch, I'm referring to this. It's level sensitive. You see, C is 1, C is 0. When C is 0, I store. When C is 1, I can change. That is level sensitive behavior. So each of them are all those things. So in this guy, I have 4 2-input NAND gates plus 1 NOT gate. Over here, I have 4 2-input NAND gates and then 1 NOT gate. Now, before I go into the analysis of this, let us all agree again about the characteristic table of the D latch. The characteristic table of the D latch says I have two inputs, D and C, and I'm monitoring the next state output Q plus. If my C input is 0, no matter what D is, Q plus will equal Q. I will be in the store state, which is written over here. Q plus will equal Q when C is 0. That's my store state. When C is 1, in the second and the third row, Q plus will follow D. So 0 will go to 0, 1 will go to 1. So Q plus will equal D. As you can see here, this column exactly matches that column. Q plus equals D when C is 1. And for this guy, it is going to be that. It is very helpful for me to write this as statements. So I have written them. Q plus follows D when C is 1. That's that. And then I've written the statement for the next case. Q plus is stored when C is 0. The reason why I'm doing this is because I will have to apply this analysis to the first latch and the second latch, which can become quite tricky. So let's do this. Let us analyze the first latch first. So this first latch is right there. That's your D latch. You see, the C input here is actually clock complement, right? So C input here is clock inverted. Inverted clock goes to C input. So if I need to say QM, right, this is QM, the intermediate Q. QM follows D when C is 1. How am I writing that? I'm simply writing that based on the statement that I wrote here. Q plus follows D when C is 1, right? So QM, for the first latch, QM follows D when C is 1. I can say the same thing, C is 1, by saying clock is 0, right? Because clock and C are complements of each other because of the presence of the NOT gate. So C is 1 is the same as clock is 0. So I can say QM follows D when clock equals 0. You guys agree with that for the first latch? In the similar manner, I can now look at the second latch, which is the slave latch. Over here, my input is QM, but my output is Q. Let me write that same statement again. Q follows QM, right? Q follows QM when C is 1. And C is 1 is the same as saying clock is 1. So Q follows QM when C is 1 or clock is 1. Now just focus on these two statements. QM follows QM follows D when clock is 0. Q follows QM when clock is 1. You see what is happening here. One guy is sensitive to the low level of clock. The other guy is sensitive to the high level of the clock. So by connecting them back to back, we have made the overall design sensitive to the positive edge of the clock when the clock is going from 0 to 1. You guys see that? So this is how we design a positive edge triggered data flip-flop. Why is it called a flip-flop? It's because it's edge sensitive. Why is it called positive edge triggered? Because it is being triggered by the positive edge of the clock input. Why is it called data? Because whatever goes in comes out. Now using this, let us try to draw the symbol of the positive edge triggered D flip-flop here. You have two inputs, one is data, one is clock, and that particular triangle indicates edge triggering. And in this case, there is no bubble in front of the triangle, which indicates it is positive edge triggered. So the triangle indicates edge triggering. So for all flip-flops, you should see those triangles that were not there in the case of latch symbols. And I can check that. I can go to any latch. Let's see. I can go to this latch. No triangle, right? But a triangle is there over here. The outputs are Q and Q complement, because you have Q and Qn at the end of the slave. Let's go back. So the behavior of this positive edge triggered flip-flop is captured using the next state table over here. When D is 1 and you have a positive edge on the clock, then you get Q as 0. When you have D as 1 and you get a positive edge on the clock, Q is 1. So both those statements say Q follows D when the clock goes from low to high. So when is Q changing? It changes only when clock goes from low to high. It's positive edge triggered. And what does it change to? Well, it just follows D input because it's a data latch. However, if you have clock at 0 or 1, and in fact, I can also add the negative edge of the clock. So if the clock is 0 or the clock is 1 or there's a negative edge of the clock, for all those times, no matter what D is, my output is going to be stored. That's positive edge triggered behavior. When I get a positive edge, my output can change. For all the other times, output cannot change. It is stored. So let me just write this over here. This indicates store. Now, this is the same master-slave configuration. And what I've done over here is I've simply drawn the timing diagrams for D, clock, QM, Q, and Qn. So let me show you guys where these are. D is right here. Clock is right here. QM is right here. Now, let us try to sketch, if not everything, a little bit of the first three. What can I say about the first latch? I said when clock is zero, C will be 1. When C is 1, QM follows D. And then when clock is 1, QM is stored. That's for the first latch. So let us try to highlight these times. Clock is 0. Where is that? 0, 0, 0, and 0. Right? So for all those times, for clock, QM will follow D. Let us see if that is the case. D is going low to high, QM is going low to high. D is doing this, this, this. It is also doing that. It is going high to low, it is going high to low. It is going low to high, it is going low to high. You guys see that? So for all the yellow regions, QM followed D. Then for all the other times, it should have been stored, right? For all the other times, it should have been stored. So stored, right? That means cannot change. It remains there. So I hope you see that with the first three timing diagrams, we were able to analyze the master latch. With those two statements, clock is 0, QM follows D. Clock is 1, QM is stored. You guys comfortable with the first three timing waveforms? All right, so let's take a look at the next one. So for the slave, my input becomes QM. My clock is simply inverted, right? So for the second one, I'm going to have to write this. When clock, earlier I said clock is 0, QM follows D. Now I'm going to need to write when clock is 1, Q follows QM. And I'm going to say clock is 0, Q is stored. That's for the second latch, the slave latch. If I apply this onto QM clock to write Q, I will get that particular graph. So let us try to see here. What can I do? Clock is 1. So where is clock 1? Maybe I need a different color. I will use green for clock 1. Clock is 1 here, clock is 1 here, clock is 1 here, clock is 1 here. So for all those times, output follows QM. So QM was doing high over there, so it is doing high over here. QM was doing, hold on. Yes, so clock is high, QM is low, this guy is low. QM is low, this guy is low. QM is high, this guy is high. You guys see that? So for all the other times, it is stored. What does stored means? It remains the same. Remains the same, remains the same, remains the same. Now once we analyze each latch, try to zoom out of this and answer this question. When is Q changing? When is Q changing with respect to clock? What is the relationship between change in Q and clock? You see this? I'm going to indicate that with some, maybe a different color, maybe brown. There are a few changes in Q. I'm going to highlight them. Oh my gosh. one is right here, and the next change in Q happens there. The next change in Q happens there. What is common to those changes? Clock positive edge. Yes, absolutely right. Those times are exactly matching with the positive edge of the clock. There was another change possible here, but we didn't get that change. It didn't change, so we didn't get it. So I hope you agree that that is exactly how we designed a positive edge triggered data flip-flop. The output was able to change only when the clock was going from low to high. Overall, it didn't change because QM was already 0. So think about it like this. There is one guy that is latching D and the other guy that is latching the output of the first latch. So because things are happening one after the other and they are latching things based on high level of the clock and then, low level of the clock and then high level of the clock. So the overall thing is responding for when the clock goes from low to high. If clock stays on, QM changes, will Q stay unchanged? If clock stays on, if clock stays on, Q will not change, like nothing will change. In order for flip-flops to be able to change from one state to the other, clock has to go low, high, low, high. It has to have an edge. In this case, it has to have a positive edge. Will Q stay unchanged? Yeah, Q will stay unchanged. Yep, you're right. Absolutely right. No change. Because when clock is 1, Q follows QM. When clock is 1, no. When clock is 1, Q follows QM, but QM itself is not changing, right? Because QM is stored. Can QM not change if clock is 1? Your QM is stored when clock is 1. So it's like we are doing the latching one after the other, which is what is making the whole thing work at the positive edge. All right. Let us stop recording over here.